All right, so let's talk about, just quickly about implementing some of this stuff in Python. So this is the code to do the edge detection stuff. So let's see. So this is how we would do it in PyTorch. We already saw how to do it in SciPy Signal. Okay, so we have to set things up for the right sizes in PyTorch. So let's establish how many images we're working with. Basically, like how many images are in our batch? Just one, just this guy. How many input channels? Grayscale, so it's one. So the batch shape is going to be like this: number of images, comma number of channels, comma number of rows, number of columns. And number of rows and number of columns we can get from im.shape. And that's 512 by 512. And so now what we're going to do is we're going to take this this is our image, we're going to reshape it according to this 4-way tensor size. And so originally the image was just a 5 by 512 by 512 matrix. Once you reshape it, it's this 4-way tensor that has shape 1, 1, 512 by 512, right? So it takes the same amount of memory to store it. It's just like now PyTorch knows that this is a 4-way tensor, whereas if you just gave it something that's 512 by 512, it would not be able to know what to do with it. It'd be like, well, you only told me 2 of the 4 dimensions. What are the rest? Okay, so creating convolutional layers. Okay, we know how to create them in NumPy. So then the way that we work with PyTorch is we could start by building a 2D convolution. So this is the neural network library in PyTorch. When we create this, instantiate this, we have to tell it how many input channels, how many output channels, and what's the kernel size. So we're going to do both of these simultaneously in one layer. So number of input channels, since it's a grayscale image, will be 1, but we're going to have 2 output channels because we're going to get the 2 different gradient operators. The kernel size is just going to be 3 by 3. We can do that by gx.shape. Okay, so now we have this thing that's instantiated in PyTorch, and when you do this in PyTorch, it just randomly initializes all the weights and the bias. So what we're going to do next is we're going to extract them from the model using this state dictionary thing, model.stateDictionary. Then we unpack them from the state dictionary. The weight, we'll call it W. The bias, we'll call it B. And then we're going to replace the values in W and B with these GXs. But of course, we have to convert GX from NumPy to a torch tensor. And then we're going to stick this into these are our 2 different output channels, and they both have the same, there's only 1 input channel. And we're going to replace all the other elements with that 3 by 3 matrix. And we do that for these 2 different output channels. We're going to use bias of 0. We don't want to shift the image at all. So now we have things set up in W and B. Now we got to put them back into our state dictionary, and we got to load the state dictionary back into the model. And now the model's set up. Now we're ready to process the data. Because the data is the right size and it's a torch tensor, our model will know what to do with it. It's as simple as this, and then what comes out is going to be a tensor that has 2 different images, and one of them will be the vertical edges, one is the horizontal edges. In order to plot it, we have to bring things back to NumPy with this detach. But finally, when we're back in NumPy, then we need to convert from these 4-way tensors back to 2-way matrices that we can plot, and we get these images just like we would expect. And these are exactly the same ones we got from Correlate 2D, not from Convolve 2D, right? Because we're actually doing correlation, not convolution. Even though PyTorch calls it convolution, it's really correlation.